everyone, and welcome to United Astronomy Clubs of New Jersey. So, unfortunately, with the weather passing through New Jersey today, we had to cancel our in-person viewing of this program. But luckily, we are still doing it online, and I hope everyone who has signed up for tickets or for reservations through the Eventbrite system, with details for that on our website, UACNJ.org, has gotten the email saying that we are still streaming this live on YouTube. I welcome everyone who has managed to join us so far, because I do notice a couple of you in chat have waved hi. So just a couple things. We, like I said, normally we would be streaming this on our webs or on YouTube, and have the in-person presentation where after we would have live viewing through the telescopes, weather permitting. Unfortunately, weather did not permit today. It in fact said, no, you shall not pass. So tonight we are having a presentation with our very own board member, Kevin Conod. He is the former planetarium manager for the Newark Museum. He is graduated from Stony Brook University in 1989 with a Bachelor of Science degree in astronomy. He is actively involved with local astronomy clubs such as the United Astronomy Clubs of New Jersey, and is currently serving as president of the North Jersey Astronomical Group. Since 1999, he has written the popular Jersey Skies column for NewJersey.com, which can be viewed on jerseysbest.com. And tonight's presentation is Reaching for the Edge, an update on the James Webb Space Telescope, which is the newest NASA telescope scheduled to launch this fall. And once in orbit, it will be the largest ever flown in space. And using this amazing instrument, astronomers will explore everything from star formation and exoplanets to cosmology and the most distant objects in the universe. And with that, I bring you Kevin.
Okay, great. Well, thank you very much, Kim. Very nice to be broadcasting to you live from Morris County instead of Jenny Jump State Forest, thanks to the weather. In fact, you might hear some rumbling in the background as the thunderstorms roll through Morris County. So, I'm going to talk tonight about the James Webb Space Telescope, which is a project that has been going on for quite some time and is one of the biggest projects that has been biggest astronomy projects in many, many years. And so it's finally coming to fruition, hopefully, this fall. And so I'm going to talk a little bit about the James Webb Space Telescope, but I thought I'd mention, because it's been in the news, the Hubble Space Telescope. A lot of people know of the Hubble Space Telescope. It's probably the most famous telescope around, and it has been in orbit for more than 30 years now. And I just thought I'd remind you here at the beginning, before I mention the Hubble, that Hubble kind of gets the lion's share of all the news clippings and that sort of thing. There's a lot of attention paid to Hubble, and so it's a bit of a media hog. You have to remember, though, that the Hubble Space Telescope was part of a whole fleet of space telescopes that was launched by NASA, and this program was known collectively as the Great Observatories, and boy, they were really great. You had the Hubble Space Telescope launching in, I believe it was 1990, and that was followed by the CGRO over on the left-hand side here is the Compton Gamma Ray Observatory, the Chandra X-ray Telescope, and the Spitzer Infrared Telescope. And so these telescopes are great because they covered a huge part of the spectrum. Hubble Space Telescope focusing on the visible light that we're used to, but Spitzer focused on infrared, Chandra on the X-ray, and Compton on the gamma ray part of the spectrum here. And so you have this very nice suite of instruments flying there in space, all at the more or less at the same time, looking at the universe in all of these different wavelengths of light. And so really a great project, a sort of multi-spectral project that was really quite amazing. Of these telescopes, only the Hubble and Chandra are still operating. So we've got these two spacecraft are still running. Spitzer ran all the way up until about a year and a half ago. They had an extended mission and continued to use it for various little projects until finally they didn't need to shut that down. So we still have two of those spacecraft still operating. Now, as you may have heard in the news, Hubble Space Telescope has been in trouble. As mentioned, it's been in orbit for a long time now, 31 years, more than 31 years now. And about a month ago, it's been out of commission now for about a month. They had a problem with a control computer on board, and so that knocked it out of operations for about a month. And that was kind of scary. They tried a backup computer and it didn't quite work. Things didn't quite work out the way they had hoped. And finally, though, they did trace the problem down to a power supply. And just this week, on Thursday, I believe it was, they did completed their tests and they were able to switch to a backup power supply and a backup section of this control unit. And they were able to reestablish communications with the scientific instruments. And so the Hubble Space Telescope is back in operation. And so that's great news, because this is a tremendously important telescope to astronomy, even though it's relatively old and kind of small. It is still a very important instrument, and so it is back in operations. But of course, nothing lasts forever, and so for the time being, it's back in operation. Hopefully, it will be operating for a couple of more years at least. And so this is where the James Webb Space Telescope comes in. James Webb Telescope has been under construction for many years, and there's been lots of delays. It's a very complicated and expensive project. And as I mentioned, it's finally coming to fruition. And so this is going to be the latest space telescope that NASA is going to launch. But I think a very important thing to recognize with this telescope is that this is not really a replacement of the Hubble Space Telescope. This is a very different type of telescope, as hopefully you will see as we go through this presentation. And there are some specific reasons for that. There are some specific reasons why this telescope had to be different in order to expand on the science that the Hubble Space Telescope has done. We need to really move into another realm of astronomy here. And so let's talk a little bit about the science that it's going to be doing. Of course, just like the Hubble, we want to do some cosmology with this telescope. We want to learn about the early universe. We've learned quite a lot with Hubble, but the Hubble is kind of reaching its limits. It's just kind of too small to look further out into the universe. And so we need a bigger space telescope to reach further out into the universe. And of course, something that really spectacular the Hubble has done is taking very high resolution, very detailed images of galaxies. And so we would like to continue that and probe back further. We'd like to see very early galaxies. And likewise, with stars, we've learned a lot about stars with our ground-based telescopes and various space telescopes. We've learned a lot about stars and the life of stars. But we'd really like to see the first stars. What were the first stars in the universe? What did those early stars look like? And so we'd like to investigate that. And we'd also like to investigate planets that are orbiting around those stars, exoplanets, the planets orbiting stars around us. We'd like to learn more about those and how they form. And so that's not the only thing that the James Webb Space Telescope will be doing, but that's the four main themes for the scientific explorations that the telescope is doing. And so a lot of those observations will center on that science. I have a little video here for you. This is just a kind of very short little video that NASA put together to get people excited about the launch of the James Webb Space Telescope.
Hey Kevin, by
Yeah.
any chance, does that video have audio? Because we are currently not getting that audio.
Oh, can you hear that? Can you hear that? Okay. There's a little overview of the project there, and as mentioned, this is a little bit of a different kind of space telescope. As mentioned earlier, the Hubble Space Telescope focused mostly on the visible part of the spectrum. It goes a little bit into the ultraviolet and a little bit into the infrared, but basically it's mostly focused on visible light. The Spitzer Space Telescope, which I mentioned earlier, that focused on some of the far infrared part of the spectrum, but the James Webb Space Telescope focuses on the stuff that's in between, what they call the near infrared and the mid infrared part of the spectrum. And as we go through this presentation, hopefully it will be clear why that's necessary. As mentioned, the Hubble Space Telescope is actually not really a very large telescope. You're talking a 2.4 meter diameter mirror. And so here you see down in the bottom left corner a circle. This circle here represents the mirror of the Hubble Space Telescope. Even when it was launched, this is really not considered a very large telescope. And the reason why they couldn't build it larger was that, well, that's the biggest thing you could fit in the bay of a space shuttle. You couldn't fit anything bigger, and so they were limited by the size of the space shuttle in order to launch this. Now, we really do need a much bigger mirror in order to probe further out into the universe. We need a bigger mirror to collect more light. And so the Webb Space Telescope's mirror will be 6.5 meters in diameter. And so it's, I think, 6 times the light collecting area of the Hubble. And so it's a much, much larger telescope. And overall, of course, it is a fairly large spacecraft. When you include the sun shield of the spacecraft, which we'll talk about in a moment, it's almost 70 feet long. So to give you an idea of how big this spacecraft is, it's about the size of a tennis court. So the next time you go out to a local park, look at the tennis court, and that's about how big the James Webb Space Telescope will be. So it's a fairly large object. And so that creates a bit of a problem. Just as the Hubble Space Telescope was limited by the size of the space shuttle, the Webb Space Telescope is also limited by the size of our launch vehicles. And so the challenge was, how do you get something that's 6.5 meters wide, which is a little over 21 feet? how do you fit that inside of a rocket? The space shuttles are no longer flying, so you have to use another rocket of some kind. And so the largest that was available when we started designing the James Webb Space Telescope was a European rocket, the Ariane 5. And so, but still you have the diameter of that rocket, if I remember correctly, is something like 18 feet across or something like that. And so how do you fit something that's 70 feet long and has a 21-foot wide mirror? How do you fit it into that little space? And so the answer is you have to build an origami telescope. And so you got to fold this darn thing up. And so this is an extraordinarily difficult project, and one of the reasons why it's taken so long to build this and why it's been so expensive, because it took years and years and years of research and development in order to build something like this that will fold up small enough to fit into a rocket like this. And so here's an artist's rendition of what the launch might look like later on this fall. You've got this fairing protecting the spacecraft during launch, but once you're out in orbit, it releases and the telescope will unfold and begin operations. And so a very tricky project, very complicated project, tricky engineering that goes into this. By the way, a little word about the optics of the telescope. That's, of course, the most important part of this spacecraft is the optics. The design is known as an anti-stigmat. This is an anti-stigmat design, which involves the primary mirror. That's the big mirror that's doing all the collecting. The primary mirror is a concave mirror. The secondary mirror up here is convex, and then there's a third mirror located down in this area, which does the final corrections. And so this type of design is very high quality. It provides a wide field of view, but it's free of some of the distortions that other designs are prone to. And so this is even nicer design than the one used for the Hubble Space Telescope. And so very nice design, and really a very challenging project to build a telescope this big. And speaking of the mirror, as I mentioned, you're talking something that is, a little bit more than 21 feet across. It's very large, and is also subject to a lot of different temperatures. And so you need a material that's going to keep its shape even under those wide range of temperatures that it's exposed to. And so they decided to build this mirror out of beryllium. And so this is a metal. Beryllium is very lightweight, but it's strong, and it resists those thermal changes very, very well. And so this is a mirror that is made out of 18 segments, and each of those segments are a little bit over 4 feet in diameter. And even though it's 21 feet across, it only weighs about 1,500 pounds. And so it's very big, but strong and lightweight. And so really quite an amazing piece of optics there. I have a little diagram that shows you the back of the mirror, one of the mirror segments. And so you've got these 18 hexagon-shaped mirrors, and there are little actuator motors on the back that will move the mirrors into proper alignment. And once they're in their, once they're in their final alignment, they are aligned to a precision of 1/10,000th of the thickness of a human hair. And so very high precision surface here for this telescope. So even though this mirror is about 6 times larger than the Hubble Space Telescope, it weighs half as much. And so it is really quite lightweight. And as mentioned, it folds. And here's an example. Here's a shot of the telescope in, I guess, in one part of its testing phases. You've got the mirror, and you've got 2 rows of these hexagons will fold back away, and that makes the telescope narrow enough to fit inside the body of the rocket. So really quite a complicated project to make something like this possible. Now, once the James Webb is launched, well, where is it going? It's not going to be in Earth orbit the way that the Hubble Space Telescope is. This is an infrared telescope. We want to focus on the infrared spectrum, which means that the Earth and the Moon are kind of would interfere with those observations because they give off heat, and that would ruin the observations. And so you've got to get this spacecraft away from the Earth and a little bit to a certain extent the Sun, but you still need it close enough that you can communicate with it easily. And so it happens that there are these points in space around the Earth's orbit called Lagrange points. And there's 5 of them. You see here they're labeled L1 through L5. And L4 and L5 are are fairly stable, but the engineers and scientists picked L2, the one behind the Earth on the far side from the Earth from the Sun, as to be the spot where the James Webb Space Telescope will orbit. And so that's where it's going. It's going out to the L2 point, and it will it won't be just sitting there. It will be in a little orbit. They call it a halo orbit, this little orbit around this L2 point, which is nice and stable. And it's you can keep your spacecraft in this position or in this orbit with very little fuel expenditure. It's very efficient to keep a spacecraft in this little orbit here. And so that's where the Webb Space Telescope is going, out to this L2 point, which is almost a million miles away from the Earth. And so it'll be, not an Earth orbit, but it'll be out orbiting with the Earth in a way, beyond the orbit of the Earth. And so it'll be sitting in that nice little L2 halo orbit. Now, because we do need to keep the spacecraft cool, the spacecraft needs a sun shield. And so here you can see the sun shield being tested and built here. And as I mentioned, it's pretty big, almost 70 feet long. And this is necessary to keep the optics and instruments for this infrared space telescope cool. We want to shield it from sunlight. And the temperature on the back side of this shield is going to be something like on the order of 300 degrees below zero, while the other half of this other half that's facing the sun is going to be like 200 degrees. And so there's a pretty big temperature difference there from one side of the spacecraft to the other. But that's what that sun shield is doing, keeping the telescope cool so it can receive these really exceedingly faint infrared signals from the farthest parts of the universe. And so really quite a feat of engineering here. By the way, this heat shield, sorry, sun shield, is made from a material called kapton. And that's a very common material used for insulation on spacecraft. It has good thermal properties. And you can see it's kind of coated with a very light coating of aluminum. That's why it's shiny. So that's what that is made of. Now, I've got another little video here. Kim, were you able to hear the audio at the latter part of that? I turned the volume up. Were you able to hear any of that? Because if not, I'll try to narrate this. Well, let me give it a shot.
Hey, Kevin,
Yes.
because the videos do not have audio, can you tell us what we are looking at currently, what this video is about? I do have a question in uh, our YouTube chat that
Oh, okay,
what are we
sure.
looking at?
Yeah. Let me turn the volume down. This this is just simply showing how the spacecraft unfolds, as it's going out to the L2 point. Over the course of several days, the pieces are unfolding as the spacecraft is traveling out to that L2 point. And so it's just simply showing you step by step the different parts that are unfolding, the sun shield extending, the secondary mirror for you can see the primary mirror unfolding, and the supports for the secondary mirror unfolding. And so that's all happening as it's traveling out to this L2 point. And so here's just a summary of what was shown in the video. And so it takes about 2 weeks after launch for it to really be fully deployed. And I believe it takes, I think it showed at the very end there, it takes about 30 days for it to finally reach its final orbit, that little halo orbit around L2. And then there's a period of testing that takes place, and I think the testing period lasts about 6 months or so. Though I'm sure we'll be getting images, sort of first light, so to speak, images from the telescope earlier than that, but the real science won't begin until testing is done, and that takes about 6 months. So that's the process that would take place over the course or take place after the launch. And once science does begin, what instruments are on board? And we've got your four main instruments, and perhaps you should count it maybe a little bit differently because they're kind of multifaceted instruments. As mentioned, though, they're all infrared. We've got infrared cameras. We have near infrared spectrograph and other types of instruments. There's two spectrographs, in fact, on board. And actually, I'll explain, if you know what a spectrograph is, we can explain that towards the end when we talk a little bit about planets. But there's also a mid-infrared instrument here that is on board this spacecraft. Oh, I'm sorry, I forgot. Kim, did you say that there was a question in the chat? If there is, maybe should we take care of that now, or could we circle back to it later?
Okay, we will have a question and answer session at the end, so I feel comfortable moving on with your
Okay.
slideshow, and we can answer any questions that arise at the end. It's just like I said, there was a bit of downtime with
Yeah.
no audio, and someone was asking what we were looking at. So,
Oh, okay. Okay. Great. So this is gives you an idea of again, going back to the spectrum, where these instruments are focused on the spectrum. And you'll notice that the near infrared instruments all dip down a little bit into the visible, but they really can only see the orange and red sort of wavelengths here, and the rest is infrared. And then you have the MIRI instrument, which does the mid-infrared part of the spectrum. And so these are all the parts of the spectrum that James Webb is focused on. As mentioned, one of the things we're really interested in is is cosmology, the history of the universe. And so the Hubble Space Telescope, this is a famous image from the Hubble Space Telescope called the Ultra Deep Field. And basically what this is that the Hubble was pointed at a part of the sky that was relatively blank. There's only a few stars here. You can probably pick them out. There's several bright stars in this field of view, but everything else is galaxies. They pointed the telescope at a relatively blank part of the sky and just simply exposed this part of the sky to one of the cameras. And they just did this for, I don't remember how many orbits, but many orbits. They were pointing at the same part of the sky and exposing again and again and again, trying to capture the most faint, the faintest things that they could. And so what you're looking at here is almost 15,000 galaxies, which is pretty amazing because this is a pretty small patch of sky. The Hubble Space Telescope is a very narrow field of view. For those of you keeping track, this square here is only about 3 arc minutes on a side. So it's a fraction of a degree. So this is a tiny little piece of sky. And yet we can see 15,000 galaxies in this one image, which is pretty incredible. You can see a very nice little spiral down in the left-hand corner here. But these are all galaxies. And so the James Webb Space Telescope, because it's bigger, we'd like to probe further into the universe. The Hubble can see galaxies that are less than 500, I think about less than 500 million years after the Big Bang. So that's how far back we can see, only about 500 million years after the Big Bang. We'd like to be closer. We'd like to reach a little bit closer to the Big Bang. And so we need a bigger telescope. And we also need a telescope that looks into the infrared. And there's a really interesting thing that sometimes gets people a little confused. It's sometimes known as look-back time or cosmic time. We really would want to see the first light in the universe. So this is the kind of known as the quest for first light. We'd like to see the earliest light in the universe. And it's an odd thing with the universe that when you look further out into space, you're looking back in time, which kind of seems impossible, but maybe you can think of it this way. If let's say you're reading something on social media, you read something interesting on a tweet, let's say a tweet. Well, you want to share it with a friend of yours who lives in California. And so you print out the tweet on a piece of paper and you put it in an envelope and you put a stamp on it and you mail it to them. And it takes a few days, perhaps these days, several days to get to California. By the time your friend opens it, he opens it up and says, oh, well, this is a week old. Why is he sending me this old news? And that's really what's happening in the universe here. Light can't travel infinitely fast. Light has a speed limit. It travels very, very fast by our standards, 186,000 miles per second. And so, excuse me, light is very, very fast, but it's not infinitely fast. And so the universe is so large that it takes time for light to reach us. And so some of that light, the most distant light that we can see is 13.8 billion years old. And so that's what look-back time is. The further out you look, the further back in time you're looking. And so that's a very useful thing for us because we can probe the origins of the universe by looking further and further back. And if we want to look at some of those most distant galaxies in the universe, well, the light that's coming from there is what we call redshifted. And this is very similar to listening to a siren. If you hear an ambulance or a fire truck zooming down a local street, as it comes towards you, the sound, the pitch of the sound goes up. But then when it passes you, what happens? The sound goes down. The frequency of the sound drops. And so those sound waves are being kind of stretched out, so to speak. And that's what happens in the universe to light. It's stretched out by the expansion of space. The universe is expanding around us. And so this light is stretched out. And when you do that to light, it shifts to the red end of the spectrum. And so if we want to see those most distant galaxies, we need a telescope that's bigger than Hubble, and we need to look further into the infrared in order to see those galaxies. And so that's a very important reason why this telescope needed to be an infrared telescope. And of course, looking at these galaxies, that's one thing that Hubble has been doing over the past 30 years, is sending back spectacular detailed images of galaxies. Here's a beautiful galaxy in, I think this is in the constellation Pisces, a beautiful spiral galaxy. And so we'd love to see some of these galaxies. And if we can see further back in time, we can see what these galaxies what they look like very early on in the universe. And as we look around us, if we look at images like the Hubble Deep Field and Ultra Deep Field, we can see that there's a lot of different kinds of galaxies. We have a kind of a biased opinion. We really, I think most people like spiral galaxies because of the beautiful shape to them, and we live inside a spiral galaxy called the Milky Way. But that's not the only type of galaxy, and there's a lot of types of different shapes of galaxies out there. You can kind of break them down into three basic groups. You've got your spirals, like the Milky Way, or like M101. It's a popular object for amateur astronomers. There's also elliptical galaxies, which range from being shaped like a globe to a spheroid elliptical galaxies like this. And so you've got a couple examples of each type here. You also have irregular galaxies that are just kind of amorphous. They have gas and dust kind of scattered all around. So they come in different sizes and shapes. And a lot of these galaxies, elliptical and spiral galaxies, are actually the result of collisions and mergers between galaxies. And that's something new that we've discovered with the Hubble Space Telescope and also ground-based telescopes too, is that these galaxies can, due to gravity, can attract each other and run into each other and merge. And our own Milky Way is the result of mergers or even several mergers. And so this is something, this is how you build a galaxy. And so we really want to learn more about this and what the early galaxies looked like to get the universe to be the way it is today. And so that's something we're very interested in, seeing the evolution of galaxies. Something else that's been really important that the Hubble Space Telescope has worked on is finding black holes, supermassive black holes at the centers of galaxies. And so that's something that is relatively new. And we think that just about all big galaxies probably have supermassive black holes. Our own Milky Way probably has a supermassive black hole in it. And so that's an area of research that James Webb Space Telescope can deal with as well. Another area of research involves dark matter, perhaps you've heard of. Dark matter is a little bit of an embarrassing topic in astronomy. You take all the matter in the universe and kind of bunch it together. About 80% of it is this so-called dark matter. Only about 20% of it is regular matter, the ordinary stars and galaxies and dust and gas, everything that we think of, and ourselves, of course, too, are part of that. When we look around the universe, we think of about the regular matter, but that's only a small fraction of what is out there. And 80% of the universe is this sort of unknown, probably particle. And we'd really like to know. It's kind of embarrassing that we don't know what 80% of the universe is made of. And so that's something that part of the research that James Webb Space Telescope will be doing, trying to figure out what this dark matter is. And so here's a Hubble Space Telescope. Here's an example Hubble Space Telescope image. The images of the galaxies here. This is a galaxy cluster. And that's a real image from the Hubble Space Telescope. But this cloudy material all around it, this is a calculation, a computer simulation of what the dark matter might look like inside this cluster. And so whatever these particles are, this is how it's bunched up inside this cluster. And so we don't know what it is, but we can see the effects of this dark matter in the universe around us. And we'd really like to know what this stuff is. And of course, excuse me, when we look out at the nighttime sky, especially if we're away from the city lights, we can see the Milky Way, our own galaxy, the stars from that galaxy streaking across the sky. And especially this time of year, when you look south towards the constellations of Sagittarius and Scorpius, you're looking towards the core of the Milky Way. So you're looking towards the core of our Milky Way here in the summertime sky, in the southern sky in the summer. And we'd like to probe the core of our own Milky Way. We'd like to learn a little bit more about that supermassive black hole that's located down near the front of the constellation Sagittarius. And so we'd like to learn more about that. Unfortunately, our Milky Way is full of gas and dust, and you can see that in the Milky Way. And it blocks our view. But fortunately, infrared light, being long wavelength, will pass through that dust and won't be affected by it, won't be scattered by it. And so that allows us to peer deeper into our own Milky Way. So not only can we look further out into space, we can look deeper into our own Milky Way using that infrared light. And of course, speaking of the Milky Way is filled with stars. That's the most obvious part of the universe, I would think. So we can look out on a nice night and see these beautiful stars. And we've learned quite a lot about stars over the years with ground-based and space telescopes. We've learned a lot about their lifetimes, how they end in supernovas and black holes and things like that. But we'd really like to know exactly how stars are born. We have some pretty good ideas, or a pretty good idea how it happens. We'd like to learn a little bit more about how the birth of a star is triggered. We know that they form in nebulas like this. There's a very famous Hubble Space Telescope image. This is part of the Eagle Nebula, and it has a nickname. It's called the Pillars of Creation, because this is a place where stars are being born inside these clouds of gas. And so we can see hints of young stars forming in here, but we can't see inside. We need some infrared light to help us see inside nebulas like this. We've done pretty good with the Hubble Space Telescope. If you look at the famous Orion Nebula in the wintertime sky, we've found very young stars. I think there's about 30 very young stars. And these little blobs of gas that you see here are called proplyds. And so these proplyds are forming stars. These are baby stars, embryos of stars forming here inside of the Orion Nebula. It's kind of a little stellar nursery there in the constellation Orion. And so we found these with the Hubble Space Telescope, but we'd like to be able to probe inside of these proplyds to find out more. And this is a good example. Here we have the Hubble Space Telescope on the left, and here we have, I believe this uses data from the Spitzer Space Telescope, which I mentioned is also infrared, and you can see inside of some of these clouds and see a little bit more about what's going on inside of these clouds as these stars are forming. And so we'd like to learn a lot more about that. And speaking of the Spitzer, here's an example of an infrared image. And so maybe this gives you some idea of what the images from the new James Webb Space Telescope will look like. We can't see infrared. We can certainly feel it. But we can't see infrared light, and so you do have to use some false colors in order to be able to make this visual representation of the images, the observations that are taking place on board the spacecraft. And so this again is this might be, if I remember correctly, is in the southern hemisphere. This might be the Carina Nebula, or nearby to the Carina Nebula, and is again a very powerful star-forming region. And so you can see all little blobs of gas here that are likely young stars that are forming here. So star formation is a very important part of research. And of course, if you're going to study the birth of stars, you're also going to learn about planets because there are planets forming around a lot of these stars. And that's another area of research we'd really like to know more about, these exoplanets, these planets beyond our solar system orbiting in these other star systems. And so that's another very active area of research, and the Webb Space Telescope will help us with those observations. And so this is what, again, an artist, not a real image, but an artist rendition of what we want to probe. These young stars are surrounded by disks of dust and gas, and this is where planetary formation would take place. And so in order to peer into these areas close to these young stars, you need, again, that infrared light to pierce the veil of dust and gas that is shrouding these very young stars. And so, again, very important reason to be using infrared. Another really cool thing about this is that we have discovered over the past several years some very interesting exoplanets. Some of them are Earth-sized. Some of them seem to have atmospheres, and they're very interesting to us. But we'd like to learn more about them. We can make some pretty good measurements and educated guesses about their sizes, but we need a bigger telescope in order to really get more information about these objects orbiting around nearby stars. And this here is a list of potentially habitable exoplanets. They are ranging from very close by in our neighborhood, Proxima Centauri, the closest star system to us. There is a exoplanet only 4.2 light years away from this. That's kind of neat. But we'd really like to find, the ultimate goal is to find an Earth-like planet, one that has an atmosphere that is habitable. And in order to do that, we need to use a spectrograph. And that's what those two spectrographs that are on board of the Webb Space Telescope will be doing. They'll be probing the atmospheres of exoplanets. And so you might wonder, well, what is a spectrograph? How do they work? CDs are not very common these days, but you have a compact disc around, pull it out, and hold it up to the light. If you've never done that, you'll notice that you get a nice little rainbow effect. And that's because of the very fine grading on the surface of that CD. And that's what astronomers use, a very, very super fine grading in the spectrograph. Light comes down from a target, whether it's a star or an exoplanet, goes through a little slit, hits a grating, and that grating splits the light up into the rainbow of colors, and you get a nice spectrum. And a spectrum is a really great thing. It's like a fingerprint. You can use that to find out what materials are in a star, or in this case, in the atmosphere of a exoplanet. So a very powerful tool that we use for all these different projects, all these science experiments that are observations we've been talking about. Those spectrographs are useful for pretty much all of them. But in particular for exoplanets, that's really great because you should be able to detect a habitable planet. In fact, actually, even with the Hubble Space Telescope, we've had some tantalizing measurements with objects such as this one. This is doesn't really have a name. It's just K2-18b, which I remember correctly is about 100 light years away from us. Using the Hubble Space Telescope, astronomers were able to detect water vapor in the atmosphere of this planet. So it may not be particularly Earth-like, but it does seem to have this water vapor in its atmosphere, which is very exciting to find water out there in these planets. So a very exciting part of Webb Space Telescope's research. Another area that we'd really like to know more about is brown dwarfs. I don't know if you've ever heard of a brown dwarf. A brown dwarf is kind of a failed star. And I know actually, unfortunately, in popular astronomy, Jupiter is sometimes referred to as a failed star, and it's really not. It is way, way too small. Even though it's the biggest planet in our solar system, it's way too small. You need to have an object. If you have an object that's about a dozen times bigger than Jupiter, it's really not a planet anymore. But yet it's not big enough to be a star. We know that the smallest stars in the universe have to be about 80 times more massive than Jupiter. So you need 80 Jupiters to make a star. That's a lot of Jupiters. That's not almost a star. That's, 80 Jupiters is a lot of material. And that's what you need in order to get fusion going inside a body like this to make an actual small star. You need 80 of them. But if you don't have enough, you get a weird object called a brown dwarf. It's not a planet. It's kind of hot. It's kind of too hot to be a planet. It's giving off some infrared radiation. It's very dim, and so it doesn't really give off very much light. And so they're very hard to detect. They're very hard for us to study. And so that's where the Webb Space Telescope will come in, using an infrared light and a much larger mirror. That will help us learn a little bit more about these brown dwarfs, which are pretty mysterious. We don't know that much about them. And so we'd like to know more about them. Going back to exoplanets, one of the instruments has on board, it has this coronagraph ability to it. And you might wonder, well, what's a coronagraph? Well, if you've ever seen an eclipse, maybe you see, here's a picture that I took of the 2017 eclipse. A coronagraph is kind of an artificial eclipse. And so just like the moon covering the disk of the sun lets us to see all kinds of details around the sun, you can do the same thing with a star. You can block out the light of a star and you can see the exoplanets that are orbiting around it. Usually those exoplanets are too faint to see. The starlight just simply overwhelms your telescope. But if you block that light, then you can see those exoplanets and study them. And so it's got a chronograph on board as well, which is very nice. So when is this happening? Well, originally they had said launch, well, of course, the launch date has been pushed back several times. Remember that the construction of James Webb has actually been complete since 2017 and has undergone extensive testing and retesting since then. And so the date keeps getting pushed back, and it's very disappointing. But, you got to remember this is a very complicated spacecraft, and it's going to be 1 million miles away from Earth, or almost 1 million miles away. Once it gets out there, if there's a problem, you're kind of out of luck. It really is not very easy to, your spacecraft breaks down, you can't call AAA to come up and change your tire, so to speak. So you do need to be very, very careful about what you're launching. And so it keeps getting pushed back, but they finalized the date of October 31st, so Halloween. This is scheduled to launch. They may not be able to exactly make that schedule because the Ariane 5 rocket has a launch this summer. I forget exactly when it is, sometime soon, either later this month or early at some point in August, that launch is going to take place. And if that's successful, the European Space Agency needs some time to get ready for the next launch. And I believe the turnover time is about 4 months. And so they're thinking that if it's not going to launch on October 31st, it will launch in early November. So we'll have to see how that goes. Hopefully we'll be able to get this launched before the end of the year. Fortunately for this type of a spacecraft, you don't have a specific window. You have a fairly open window, and you can launch at any time to get out to your L2 point. You don't have to worry about the positions of the planets in that case. So a pretty wide open window, and hopefully that will happen soon. And as mentioned, it will launch out. The fairing, the covering of the spacecraft will be dropped off, and the spacecraft will unfold as it reaches out towards that L2 point. And so as mentioned, the Hubble Space Telescope is back in operation, and so that's great. Hopefully it'll be operating for a few more years. And so both the Hubble Space Telescope and the James Webb Telescope will operate in tandem. And that's nice because we'll be able to cover a fairly large part of the spectrum, from the mid-infrared up to the near ultraviolet part of the spectrum that Hubble can reach. And so these two spacecraft will be working together on many projects. And so this is really exciting time for astronomers, and hopefully everything will go well. Now, I'm almost at the end of my talk here, and I thought I'd mention that something that's been burbling in the background. The James Webb Space Telescope, it was named after this person, James Webb. You might wonder, who the heck is this guy? James Webb was an administrator of NASA during the Apollo program. And I remember when they announced this, when they announced that they were naming this telescope after James Webb, I thought, boy, it's a little odd, because most of our telescopes are named after astronomers and people who have some connection to astronomy. And I thought, oh, well, that's kind of nice. They're naming after this administrator. But I thought it was a little odd to name it after a bureaucrat, But, well, that's what they did. Well, there's been a lot of talk recently that people have become unhappy with this name. Because there's a little connection here. James Webb, early in his career, had an involvement in something called the Lavender Scare. And this was not a very nice part of our history, where people who were suspected of being gay were fired from federal positions. They thought they were security risks, and they were fired. And he had a hand in this. And so people were not very happy about it. And so NASA has promised to review this at some point in the near future. They might end up renaming this telescope. And so if that's the case, think about that. If this telescope is named after someone important who has, if we rename it in connection with some astronomer, think of a famous astronomer that maybe deserves to be this telescope to be named after. So think about that. They may not decide not to do that, but to rename it. But if they do, I think we should be ready to make some good suggestions. And speaking of which, there's another space telescope here that is being built. This is a space telescope that has an unusual history. It was originally known as W First. And this is a very wide field. This is also an infrared telescope, but it's a very wide field view. This telescope will have a field of view 100 times greater than the Hubble Space Telescope. And so very wide field. And this is being built from an old spy satellite. The National Reconnaissance Organization, for whatever reason, ended up having 2 spy satellites left over that they did not want to use for anything. And they're very similar in design to the Hubble Space Telescope, but a very wide field of view. And so they made these available to NASA. So NASA grabbed them, and this first one is being built into this infrared W First telescope, which not too long ago was named after Nancy Grace Roman. So this is the Nancy Grace Roman Space Telescope. I thought that was really nice because Nancy Grace Roman, if you don't know who she was the first chief astronomer for NASA and first woman to have that position. And she held that position for a very long time and helped guide the Hubble Space Telescope to its launch. And so she was largely responsible for that, as well as another person whose name we actually already mentioned, Lyman Spitzer. If this was the mother of the space telescope, the father of the Hubble Space Telescope was Lyman Spitzer, who first suggested the idea of putting a telescope in space back in the 1940s. And he has a nice little New Jersey connection here. He spent most of his career here in Princeton, New Jersey. So he had a space telescope named after him, and now Nancy Grace Roman also has a space telescope named after her. And hopefully that will fly in 2025. That will begin to fly. So something to look forward to. And if you'd like to learn more about some of the details of the James Webb Scope, you can look at the NASA website, jwst.nasa.gov, and you can check that out online. And so that brings us to the end of our talk. And so I hope you enjoyed that and learned a little bit about this exciting project. And I believe, Kim, you said that we might have some questions here at the end of our program.
Indeed, we do actually have several questions from
Great.
the chat. So I am going to put out a call for any questions you may have remaining, you guys in chat. Please do type them into the chat you're in. And for a minute there, I'm going to, while I'm getting a couple more questions populated into the chat, go over a couple things. First of all, I want to thank you, Kevin, for giving us wonderful talk. We are a completely nonprofit and volunteer organization, so people like Kevin do volunteer their time to come down and give talks. When we are on site, we are, like I said, completely volunteer, so everyone you will see involved in this isn't getting paid, even though some of us have tried. So I want to thank everyone that you see behind the scenes, and I want to thank our viewers for coming in and showing up for our streams and whatnot. It does encourage us, especially to keep offering continued outreach and public programs like this. So we are going to start. The first question I have: is it possible with current technology and such to have a telescope that covers all of the energy and UV wavelengths rather than having 4 separate instruments like you had in a slide at the beginning of the presentation where you had Chandra, Hubble, Spitzer, and
Compton.
Yes, that one.
Right. And the short answer is no, absolutely not. It's just not possible. And the reason for that is that if you have a telescope, if you imagine a telescope like, let's say, a super Webb type telescope that would do all wavelengths, well, the mirror, you'd be able to collect, with a mirror, you can collect visible light and to a certain extent infrared. And if you design your mirror right, you can go pretty far into the infrared and also a little bit into the ultraviolet. But after you stray away from that, if you go too far in either direction, what happens is the light will pass through your telescope mirror. And so the materials that we ordinarily use, let's say a Jenny jump for our observations, they're just the wrong materials. They cannot capture, they're transparent to those wavelengths. They go right through it, or they would be absorbed by the mirror, not just pass through it. So it just is not really possible to do that. And so when you go off into the higher energy, when you go up through gamma and X-ray energies, yeah, it starts to get very difficult because, as you know, X-rays and gamma rays will pass right through a lot of materials. And so you have to have some very bizarre designs in order to capture data from those wavelengths. And it's hard to describe, but if you just look around online, look at the optical designs for something like the Compton Space Telescope or the Chandra Space Telescope, the quote-unquote mirror is not a mirror at all. It's a set of cylinders. And basically it takes those high energy photons and it bounces off these cylinders and goes into these detectors. And so very bizarre stuff. And if you go in the other direction, you go into the infrared. Well, once you go beyond the infrared, what do you get into? You're getting into microwave and radio waves. And for that, you need not a glass mirror with an aluminum surface, you need an antenna. And so you've got to build an antenna to capture that. And so you really can't have all those wavelengths in one single telescope.
All right. So basically, what we've concluded there is that you wouldn't have one instrument on the thing that does it all. You would have to have several separate instruments to do that.
Yeah. And you might be able to mount that on a single platform or so, but that'd be pretty gangly type of thing. It'd be kind of a complicated type of thing.
Yeah, especially if I would imagine if you wanted to point it at one place, so you're collecting all the data for one point in space instead of multiple points in space.
Mm-hmm. Mm-hmm. Yeah.
All right. So our next question is, why do we even have a quest for a stronger telescope? What do we hope to achieve looking so far, for example, back in time, but not necessarily being able to reach it?
I assume by that you mean, well, we can't go there. Well, yeah, of course, it's, looking back at galaxies that might be almost 14 billion years old, we could never travel 14 billion light years, so we can't go there. But if you want to understand about the universe, about where did we all come from, everything that's around us, where did this all come from? If you want to understand the universe, that's what you have to do. You've got to try to figure out what was the universe like in the past, and that would hopefully we'd understand a lot better about the universe around us. And you might say that, well, so what? That doesn't put food on the table. And no, it doesn't. But it's something that people have wondered for thousands and thousands of years. People have had these questions about where did we come from, and what does this all mean around us? And so it's just something that we're human beings are pretty curious people, and we've been wanting to answer these questions for as long as we can remember. And so it's all part of being a human being, I guess. We're very curious, and we have lots of questions, and we'd like those questions answered. And so no, it won't put food on the table, but we find this to be a very important, and I think a lot of people do find these important questions, and we wouldn't put this much effort into it if we didn't have this curiosity.
All right. The next question is actually one of my own, because
sure.
it had to do with a word you said, propylates. First of all, how do you spell it? Because my mind, having only a high school level of science, had decided that, is that what happens when lipids go professional?
It's proplyd. If I remember correctly, it's spelled PROLYD, proplyd, and I'm not quite sure what the origins of that word are, why they really particularly pick that word to describe these little blobs of gas, but maybe the shape of it reminded of some of them of something. But yeah, these are little blobs of gas that have been found in nebulas like the Orion Nebula, and so they're simply called proplyds, and so. Yeah, I don't quite remember what the word actually means. I'd have to look that up, but yeah, it is kind of an odd word, isn't it?
Yeah, I'm like, that sounds like an odd word, and it sounds very similar to biology terms. And I'm like,
Yes, yes.
man, it's been a while since I had high school biology, but I apparently still remember some of them.
And unfortunately, on occasion, I've made a mistake and said the word wrong, and it came out polyp, which is not something that you want.
Oh, that's even worse.
Yes, it's even worse.
Do not want polyps on
No,
the telescope.
no, you do not.
All right. So the next question is, when it comes to dark matter, what is the difference between dark matter and let's say the space that an astronaut might experience when stepping out of a craft, like the void they're stepping into?
Well, dark matter, again, it's kind of very mysterious. We don't really know what it is. We suspect that it's a very exotic particle and has very unique properties that make it difficult for us to study. And so this dark matter is, I mean, it's not only in space, it's here too, where it's all around us, here on Earth, inside the Earth, all the space around us. And this dark matter, um, you know, uh, doesn't really interact with very much of anything around it, or even these dark matter particles don't even interact with each other very well sometimes too, and so it makes it exceedingly difficult to understand what they are, and so it's all around us, and so when an astronaut steps out into space on a spacewalk, well, yeah, he's surrounded by dark matter particles, but so are we here on Earth on the surface. So it's not really anything different. So it's just part of the universe. And, that's, as I mentioned, it's kind of embarrassing that we don't know what 80% of the universe is. We'd really like to know what these particles are. And there's a lot of different projects, not just space telescopes. There are projects that usually, and I forget how many there are at this point, there's 3 or 4 at least, dark matter experiments happening inside the Earth. They're underground, and they're attempting to detect these particles directly, which is a very, very difficult thing to do. And so those projects are online as well. So there's various experiments going on trying to figure out what these dark matter particles are.
All right. So let's see. The next question. To give people a better understanding of just the scale we're talking about with brown dwarfs, how many Earths is a Jupiter, and how many Earths does that then make 80 Jupiters?
Oh, I don't know offhand, but you're talking about, let's say if you take Jupiter, you could fill it up. You imagine Jupiter as a gumball machine. You could fit about 1,200 Earths inside of Jupiter. And so whatever 80 times 1,200 is, you're looking almost 100,000
Hold on,
Earths.
I have an app for that.
Oh,
They said we wouldn't carry calculators in our pockets in the future, but they were wrong.
so
So that's 1,200 times 80. That's
right.
96,000
Yep,
Earths.
96,000 Earths inside, and that's the smallest star. If you think about a sun-like star, if I remember correctly, it's around 1,000,000 Earths that you could fit inside of the sun, and the sun is sort of a medium-sized star.
All right. Going back, I'm gonna skip around for a question for a minute
Sure.
because there's actually a question regarding the last one I asked. How do we know that dark matter exists, or is it just a name or a placeholder for what we're trying to figure out now?
Um, it it uh, it is kind of a placeholder, but we can see the real effects of dark matter. And I kind of skipped over. I kind of forgot to mention it, but that's okay. We can talk about it here at the end. The reason why we know about dark matter is by watching the motions of galaxies in these galaxy clusters. We can see that the galaxies don't seem to be moving quite right. And a famous example of evidence of dark matter occurred many years ago, I believe originally in the 70s. A woman named Vera Rubin was measuring stars in our own Milky Way. And she was trying to measure the rotation of our own Milky Way, the motions of stars through the Milky Way she was measuring. And when she made these measurements, she figured out that our galaxy is rotating kind of incorrectly. It doesn't quite make sense. The way it rotates does not match up with what we know about gravity. And so it was acting as if there was hidden matter in our Milky Way, and that's the effects of dark matter. And so we do see these real effects of dark matter around us, what we think is dark matter. And we've tried different types of things to try to, and a number of people have been working on projects trying to make dark matter go away. They try to modify gravity in order to explain what we see. And there are some modified versions of galaxies that of gravity that works very well, but unfortunately it only works inside of a galaxy. When I try to go outside of a galaxy, it no longer works, and that you can't have that. Gravity has to work the same everywhere in the universe. It can't work differently inside a galaxy as opposed to the rest of the universe. So that doesn't quite work either. So it's a very mysterious problem to have, and it's part of a very active area of research for astronomers and physicists, and in particular particle physicists who are working on these projects trying to detect dark matter particles.
All right. Building off of that, because now I'm curious. Now you said gravity needs to work the same everywhere. And this is going to sound really stupid, but what if gravity's like an Excel spreadsheet where it's, and if this equals true, you get this result. If this equals false, the next result? Or if then statement is what I'm looking for.
In other words, gravity would change in different parts of the universe. Is that what you mean? To be different as you?
Yeah, like it was just a curious thought that occurred to me. But what if it's an if-then statement? If in galaxy, then this. If not in galaxy, then that.
I think if that was true, the current models, I don't think there's much evidence of that. Are the computer simulations that we put together. All this data that we're collecting is fed into some of these models. And the models are certainly not perfect because we have limited understanding. But if what you were suggesting were true, I think those models would not work at all. They would be completely off, and it would be fairly obvious. So it does seem, I think most of the data we've collected so far seems to point that our assumption that gravity is the same everywhere is correct. I don't think we've seen anything that contradicts that, at least not at the moment.
All right. So the next question I have is, someone had seen the graphic where there were planets we could possibly habitate.
Sure.
And he saw that there was one 4.3 light years away.
Yeah.
Are there photos of said planet that are 4.3 light years away? And if so, is there any way to potentially predict what it would look like 4.3 light years from now, or whatever that would be equivalent to in real time, for example?
Right. Yeah, no, there are no photos of any of these objects, and I forgot to mention that these are all artists' renditions of what we think they could look like if they were habitable. And and unfortunately, off the top of my head, I don't remember the details about Proxima Centauri b. It is very close to us, as mentioned, 4.2 light years away. So it's in our neighborhood. So that's very exciting that we have a planet that's close to us that we can study. And so I'm sure with the James Webb Telescope, this planet will be very high on the list for imaging to see what we can see with this much larger telescope. But we can look at this with spectrographs currently, but there's a limited amount of information. I think that most astronomers, if I remember correctly, are kind of leaning towards the position that this planet is probably not habitable. It's orbiting around a star that is extremely small. It's a very small, dim star, and this is orbiting very close to its star. And I forget what the orbit is, but it's a very tight orbit. And so, unfortunately, for these what we call red dwarf stars, like Proxima, they're small, but they're kind of violent. They have lots of flares. So a lot of radiation pouring out and eruptions happening around these stars. They're very violent, and so this
Oh,
planet's
so it's
probably
like me when I haven't eaten.
right. It gets very hangry. This star gets very hangry, and so it makes kind of a tough environment for life to get started if you're on a planet that is bathed in this radiation. So it's not impossible. There may be lots of different types of life out there in the universe that we don't know about. But for ordinary life that we're familiar with, it'd be very difficult for life to get started on a planet like that. So probably not, but we'd like to know more. Like I said, this bigger telescope will hopefully teach us a lot more about these types of objects.
All right. Okay, so I have one more question
Great.
here. And before I ask that, I'm going to put out a last call for any last questions chat may have. It looks like this last question, someone's still hung up on the dark matter thing.
Oh, sure.
And it's if we take a pressure-proof jar into the void of space, so the mason jar on steroids,
Right.
could we capture some of this dark matter, or is it kind of just an intangible force?
Yeah, these are very intangible particles. And like I said, these dark particles are not in space. They're right here, all around us. And so you can pull out a super duper mason jar and just collect some air and seal it up. And there are dark matter particles in there. But unfortunately, the dark matter particles don't interact with matter very much, and so they would pass right outside the jar. It's just, as far as we know, almost impossible to build a jar that could contain dark matter because it's very bizarre. This stuff really does not interact with ordinary matter. It'll pass right through it. So you can't collect it very, very easily. And so that's what makes it so difficult to build instruments to detect this sort of thing. And so that's why those experiments, those particle experiments I was mentioning, are buried underground, is to protect them from other particles interfering with your experiment. These are very, very difficult detections, and so they don't happen very rarely. And so that's why these experiments are running for long periods of time. And so, yeah, that wouldn't work. You could not put a dark matter particle in a jar. There was no way to really trap them.
So it's not like Star Trek where you can just have a blob of dark. Actually, no, that's antimatter. That's a completely different thing that they tried to shoot into the son of Romulus.
Right. Yes. Right.
All right.
Antimatter we can contain. We can use that with magnetic fields. So. But not dark.
Right. So that seems like it is so far the last of our questions. Again, I want to thank you, Kevin, for giving us a great talk and a great question and answer session. A couple things to note. We are, like I said, we are open April through October, and usually every Saturday, April through October, we are live on site with the pandemic. We are doing reservations, and we are holding our lectures outside. So, of course, when it is thunderstorming and whatnot, we do have to take that into consideration. And like tonight, we were not able to do this live on site. We did have to go solely to our online program. So, we have right now, like I said, we do stream this live on YouTube. All our presentations from the past have been saved on there, so you can always view our past presentations. If you want, please do come out to our site in Hope, New Jersey, in Jenny Jump State Park. We are United Astronomy Clubs of New Jersey. Check us out on our website, uacnj.org. You can also check us out. We have a Facebook, we have Instagram, we have Twitter, although I don't think Twitter's used as much as Facebook, but please do hop on all of them because we do send out reminders whether we have closings or whether we have special events like several years ago now, we had that giant solar eclipse across the United States. We did actually have a live on-site event for that, a special event. So we would post special events such as that onto our website and likely be posted onto our Facebook. Also to note, we are a nonprofit, so any donations you guys do, which are available through all our forms of donations are available through our website, do help to keep our lights on and keep us offering free public programs. On that note, we do actually just went live today with a new form of support where it is Patreon. Patreon, as many viewers might know in the online community, is a subscription-based service where you can select a monthly recurring donation amount that does help us greatly. Keep in mind that said donation does just keep help words. Sometimes they get you need to unwrap your tongue around your eye tooth so you can see where you're speaking. They do help us keep offering programs, and those tiers of support only allow you to have the rewards as listed under those tiers of support. With that, let's check for any last minute questions. No, there's just someone being very excited and all capsing in chat that they really enjoyed the program, and our bot kind of yelled at them, "Hey, we don't need to be spam yelling in here." So with that, have a good night, Kevin, and have a good night, everyone, and thank you for coming.